Okay. My name is Yoshikazu. It is my great honor to introduce today's lecturer, Professor Ken Shirakawa of Chiba University, from Chiba University. He received PhD from Chiba University under the guidance of Professor Kenmochi in 2001. And after that, he moved to Tokyo Denki University and then stay at Kobe University. And from 2010, he moved to Chiba University. And his major field is his major tool is very reflected from this title, and he's a specialist of evolution equation, especially involving subdifferentials. And his interest is broad and including motion of grain boundary too. Today, he is going to talk about temperature optimization problem governed by semi-discrete phase field model of grain boundary motion. Please.
Thank you. Thank you for the introduction. First of all, I would like to thank the organizers of this seminar, especially Professor Giga and Professor Howell for the kind invitation and giving me a chance to talk this seminar. The title of my talk is Temperature Optimization Problems Governed by Semi-Discrete Phase Field Models of Grain Boundary Motion. This talk is based on recent joint works with Harville Until, George Mason University, USA, Shodai Kubota, Chiba University, Japan, and Noriaki Yamazaki, Kanagawa University, Japan. In this talk, we consider a class of optimal control problems governed by Kobayashi-Warren-Kata type systems. Kobayashi-Warren-Kata system is a system of partial differential equations which was proposed by Kobayashi, Warren, and Kata as a possible mathematical model of planar grain boundary motion. Let capital T be a finite and positive constant. Let omega be a bounded domain with smooth boundary. On this basis, we consider a situation such that on the product space of the time interval 0 capital T and omega, the spatial domain omega is occupied by a polycrystal, like ceramics. Here is a sample picture to get the point of such situation. This is a picture of micrography provided by UBE Scientific Analysis Laboratory. In this picture, we can see that the spatial domain is divided by small masses of crystals. These masses of crystals are called grains, and the free boundary between these grains is called grain boundary. Also, we can see that some grains have a characteristic orientation by this stripe pattern, and other grains do not have such characteristic orientation. The former phase is called oriented phase, and latter one is called disoriented. In Kobayashi-Warren-Kata system, the orientation degree of the orientation is called orientation order, and it is described by using an order parameter denoted by eta. On this basis, in this talk, we consider that if the value of eta is equal to 1 or greater than 1, then we consider it is oriented. If eta is equal to 0 or less than 0, then we consider it is disoriented. Otherwise, we consider it is intermediate. On the other hand, the angle of the crystalline orientation is described by using another order parameter denoted by theta. This is the angle of the orientation of a grain. Kobayashi-Warren-Kata system consists of two partial differential equations. The first equation is kinetic equation for eta and it is described as a heat equation with a perturbation G and forcing term U. We impose the zero Neumann boundary condition for eta, and we denote by eta sub zero the initial value of eta. On the other hand, the second equation is a governing equation for the component of theta, and it is described in form of the quasi-linear diffusion equation with unknown dependent coefficient alpha and alpha naught. These are called mobility. Here we note that the diffusion is expressed by the singular diffusion with a regularization by Laplacian of theta. We denote by V the forcing term of the second equation. Also, we impose the zero Dirichlet boundary condition for theta, and we denote by theta sub zero the initial data of the component of theta. Alpha and alpha naught are given functions. In the original study of Kobayashi Warren Carter, they did not have forcing term, and they derived the system as a gradient system of the following free energy. Here, this capital G is a potential function of the perturbation of G. However, in this time, we have the forcing terms. These forcing terms will be a control parameter, unknown control parameter in our optimal control problems. And especially, we suppose that the first component of the control is a relative temperature. In view of this, we can say that we are going to consider temperature control problem for the grain boundary. Finally, we note that the coefficient nu, the coefficient of the Laplacian of theta is a fixed positive constant. Now here is a sketch of the history of the previous studies concerned with Kobayashi-Warren-Carter type systems. A lot of previous works are devoted to the existence and lifetime behavior of the solutions to Kobayashi-Warren-Carter type system. The previous works are largely divided into the positive case of the coefficient of nu and the zero case of the coefficient of nu. Here, the positive case of nu implies the result in the active case of the Laplacian regularization of theta. On the other hand, the zero case of nu means a result in very singular case of the diffusion of the component of theta. In the meantime, for the uniqueness question, we note that there are only a few previous works, and all results are obtained only in the case of positive case of nu. Here are examples of such previous works. As a first example, we can find the result in one-dimensional case of omega. On the other hand, as a second example, we can quote the result which is discussed under eta independent case of the mobility of alpha naught. In this second previous work, omega can be considered as a higher dimensional domain, but instead of this, we must assume that this mobility is positive, bounded, and Lipschitz continuous with respect to time and spatial variables. However, in the modeling method of Kobayashi, Warren, and Carter, this mobility is required to be governed by the order parameter of eta. So, from physical point of view, this setting should be said not sufficient. However, anyway, the uniqueness question will be important for the advanced issues such as optimal control problem. In fact, as a continuation of the second previous work of uniqueness, we could obtain some results of optimal control problem. In the issue of optimal control problem, our interest will be in the existence and parameter dependence of optimal controls, and especially we are very interested in the necessary condition of optimality. However, in the physically required setting, that is the eta dependent case of alpha naught, we do not have an effective mathematical method yet. So even in one-dimensional case, the optimal control problem and the eta dependent case is still open. In view of this, we set the objective of this talk, the optimal control problem and the eta dependent case of the mobility alpha naught. To this end, we adapt the time-discrete setting. The aim of time-discrete setting will be to simplify our problem and to enable precise observation for the optimal control. Now we adapt the following time-discrete Kobayashi-Warren cut type system as the state system of our optimal control problem. In this talk, we denote by n the division number of time interval. Also, we denote by tau the time step size. Also, for simplicity, we denote by x the space of L2 functions. And we denote by bold x the space of all time sequences of L2 functions. Now, our state system is formulated as the following system of two time discretization schemes. So, in this talk, the solution to the state system and the control variables are obtained as the time sequences of L2 functions belonging to the space bold x. Here we note that this scheme could be regarded as a minimizing movement scheme. And also, we note that the coupled minimizing movements system can be solved separately in the order of the first scheme and the next second scheme. Now, on this basis, we denote by OP0 our optimal control problem and define this problem as a minimization problem of the following cost function denoted by J, U, and V. In this problem, the unknown variable is a pair of controls U and V. Also, we fix the pair of L2 time sequences denoted by eta AD and theta AD as the admissible target profile for the grain boundary. Also, for any pair of controls, we denote by eta and theta the solution to the state system. On this basis, we define the value of the cost function by the sum of the square of L2 distance between the solution to the state system and the admissible target profile and the square of the L2 norms of controls. In addition, in this problem, we suppose that the range of the control is constrained in the closed class denoted by UAD. In the constrained class UAD, we suppose the box constraint for the first component of the control. More precisely, for the temperature control, we suppose there are two bounded obstacles denoted by sigma lower star and sigma upper star And by these obstacles, the range of the temperature is constrained. So in the light of this constraint, we can call our problem temperature constraint optimal control problem. However, in this time, we should note that the singularity as in the state system brings the non-smoothness of the cost. It is not good at all in numerics or practical sense. So before we start the discussion, we will prepare the following approximating problems for our optimal control problems. In the approximating problem, the modification point is only in the point that we replace the state system by its relaxed version. In the relaxed system, the singular flux of the diffusion is regularized by using the following regular function denoted by f sub epsilon. Here, epsilon is a positive constant, and f epsilon is defined as this hyperbolic function which approximates the Euclidean norm uniformly as epsilon tending to 0. Now, by using this function, the singular flux in the diffusion of theta is regularized by the gradient of f epsilon. Now we denote by op epsilon and s epsilon the relaxed version of the optimal control problems and state system, respectively. However, we note that our original problem corresponds to the case when epsilon is equal to 0. In fact, if we assign the Euclidean norm as a function f0, then we can unify the expression of our problem by using the subdifferential of the convex function f epsilon. In fact, when epsilon is equal to 0, the subdifferential coincides with the set-valued sine function. And this subdifferential expression will give the rigorous definition of singular diffusion. Now, here is a plan of this talk. This talk is largely divided by former and latter part. Former part is devoted to the mathematical analysis for our optimal control problems by means of calculus of variation. In the former part, we will see three main theorems A, B, and C. In the main theorem A, we will see the existence and parameter dependence of optimal controls for all non-negative epsilon. In the theorem B, we will see the first of the necessary condition in the positive case of epsilon. That is a relaxed problem. In the third theorem C, we will see the limiting observation of the necessary condition as epsilon tending to 0. In the second and third theorems, the result will be obtained as a result of linearization method for the state system. And this linearization method will link to the Gato differential of the cost. The key point will be in the linearization of the diffusion term of the component of theta. In fact, when epsilon is positive, then the diffusion of the component theta is like this. This is quasi-linear diffusion. And after the linearization, the expression of diffusion is like this. This is a little bit complicated, but we can do something. However, when epsilon is equal to 0, such observation turns very difficult. In fact, when epsilon is equal to 0, the diffusion has singularity like this. And then after the linearization, what happened? We cannot say anything. So in the latter part, we focus on the one-dimensional setting of the spatial domain of omega, and we try to see the expression of the limiting necessary condition more precisely. The last theorem D is concerned with the limiting necessary condition on some neighborhood of grain boundary. This result will give some partial answer of this issue. This theorem D, last theorem D, is based on H2 regularity of the solution to the state system. And this H2 regularity is guaranteed by the decomposition property of the quadrilinear diffusion shown here. Now here are assumptions required in this talk. In this talk, we restrict the spatial dimension at most 4. Also, we fix positive constant nu. We suppose obstacles, time sequence of obstacles are bounded. Also, we denote by x the space L2, and we denote by bold x the space of all time sequences of L2 functions. Also, we use a character y. The functional space is based on h1 omega. Moreover, we add the subscription 0 for the functional spaces based on h1 0. Next, for the mobility alpha naught, we suppose that it is a fixed function of local Lipschitz, and it is positive valued. For another mobility alpha, we suppose that it is C2 function and it takes the minimum at the origin, and it is convex, and alpha never degenerate, as well as alpha naught. G is a Lipschitz perturbation having a non-negative potential capital G, and we suppose that there exist constants R lower star and R upper star satisfying this blue condition. We take the pair of initial data in the range of H1 functions, and especially for the first component, we suppose that the range of eta 0 is constrained on the closed interval R lower star and R upper star. Finally, we suppose the number of the division number n is sufficiently large to satisfy this inequality. Here we note that the conditions colored blue are for the infinity boundedness of the orientation order. Also, the final assumption A5 is for the strict coercivity of the state system. So thanks to this condition, we can solve the state system easily. Now, under these assumptions, we can prove the following proposition concerned with the solvability of the state system. For every non-negative epsilon and every pair of control, the state system admits a unique solution. Here, the solution satisfies the standard regularity of elliptic variational problem, and eta and theta satisfies this time discretization scheme in L2, and especially the first component eta satisfies the range constraint property. Eta satisfies the zero Neumann boundary condition, theta satisfies the zero Dirichlet boundary condition. Here we note that the singular diffusion is expressed by using the subdifferential of the convex function f epsilon when epsilon is equal to 0. We can prove this proposition by referring to the result of previous work. Moreover, if we don't have the forcing term, then we further verify the energy dissipation for the following sequence of free energy. Also, we can show the following proposition concerned with the continuous dependence for the state system. For every non-negative epsilon, let S epsilon be the solution operator which maps any pair of control to the corresponding solution to the state system. Then, this operator has the following continuous dependence with respect to the convergence of epsilon and the weak convergence of the controls in the topology of L2. And moreover, this continuous dependence is governed by a strong topology of H1. Now, this continuous dependence means a continuous dependence of the cost. So by using these propositions, we have the following theorem concerned with existence and parameter dependence of optimal controls. For every non-negative epsilon, we can show that the problem, our optimal control problem admits at least one optimal control. Moreover, if we take the sequence of optimal controls labeled by epsilon, then we can say that this sequence has an omega limit point for the movement of epsilon, and we can say that this omega limit point is approached in the weak topology of L2. Moreover, we can say that any omega limit point is a solution to our optimal control problem at the limit of epsilon. We can prove this theorem by applying the argument of minimizing sequence. Now next, let us see the necessary condition of the optimality. The key point will be the Gato differential of the cost, and it will be linked to the adjoint of the linearized state system. Here is the auxiliary system to see the adjoint system. In this system, we have 7 coefficients denoted by A, mu, lambda, omega, capital A, omega tilde, and lambda tilde. However, for 6 coefficients, except for mu, we can suppose that they are all bounded. For the component of mu, we will see that we can suppose that this mu is non-negative and it belongs to L2. So if the spatial dimension is lower than 4, then we can apply this Sobolev embedding and we can define this system in the framework of H1 dual. This is the principal reason why we want to restrict the spatial dimension less than or equal to 4. Here, H and K is a given forcing term. And in the case of the Gato differential of our cost, we adapt the following setting by using the solution to our state system. Here we note that this adjoint system are backward system of backward schemes for the time step, and we adapt 0 terminal condition. Also, we note that this adjoint system is solved separately in the order of the second scheme and the next first scheme. Moreover, we note that in this time, the time step size is a fixed constant. Thanks to this setting, we can treat these blue terms, including the time difference, in the framework of usual L2 functions. In fact, if it is in continuum framework, these blue terms should include time differential parameters. Then the mathematical treatment will be very tough. This blue part comes from the eta-dependent setting of the mobility of alpha node. So these blue terms will be big obstacle to try to obtain the adjoint system in the continuum framework under eta-dependent case of the mobility alpha node. Now, based on this, we can prove the following second main theorem concerned with the necessary condition of optimal control. In the regular case of the problem, we can say that the optimal control is a solution to the following constrained variational inequality governed by the temperature control class UAD. Here, the pair of P epsilon star and Z epsilon star is a solution to the following linear problem corresponding to the adjoint system. The linear system corresponds to the adjoint system of the linearized state system. This main theorem B will be useful to obtain the optimal control numerically. Here we note that for the second component of the control, we don't have any constraint. And we could have the relationship between the optimal control and the adjoint system in form of the equality. However, due to the constraint, such observation is not applicable for the first component. In fact, due to this constraint, the relationship between the optimal control and the adjoint system is given by the constraint variational inequality. However, if we use the projection onto the obstacles, we can express the relationship by means of the equality. In our case, we can say that optimal temperature control is equal to the composition of the projection onto the obstacle, and the first component of the solution to the adjoint system with negative sign. Now, by taking the limit as epsilon tending to 0, we will obtain the following main theorem, third main theorem, labeled by theorem C. As a limit of approximating optimal controls, we find an optimal control of our original problem, denoted by U circle and V circle, and we can say that this is a solution to the following constrained variational inequality. Here, the pair of P circle and Z circle is a solution to the following limiting adjoint system. The key point is as follows. For the first component, we need somehow the strong convergence of the component of P. However, since the first scheme is governed by the perturbed Poisson equation, we can have H1 boundedness of the solutions by standard way. So by applying the compactness theory of the Sobolev space, we can obtain the strong convergence of the first component. And then we can obtain the limiting relationship. of the variation and inequality. For the second component, the necessary conditions given by equality and the system is linear. So we need only weak convergences. So by using standard boundedness in H1 class, we can obtain the limiting relationship. However, we note that we still have some unclear terms denoted by Guzai circle and theta circle. This Guzai circle is somehow linked to the singular diffusion flux inner product of singular diffusion flux and the gradient of the second component of the solution to the adjoint system. On the other hand, this the component of theta circle is correspond to some diffusion of this ill-pose expression. At this stage, we cannot say what is it. It is some distribution. However, for details, we don't know yet. So now in the rest of this talk, we focus on the one-dimensional setting of the spatial domain of omega. Here, let us start with to see the advantage of the one-dimensional setting. In one-dimensional setting, we can use the compact embedding H1 Sobolev space H1 omega is embedded in the class of all continuous functions. This embedding enables us to remove the constraint of the temperature. So hereafter, we consider our problem under constraint-free setting. Next point is as follows. We can use the decomposition property of the quadrilinear diffusion. In our case, we can say that the diffusion of the component of theta can be decomposed by the sum of the singular diffusion and the second derivative of the component of theta. So in this time, we from this decomposition property, we can say that the component theta belongs to H2. This decomposition property can be obtained by referring to the previous works by Rivka and Muha. However, for the non-homogeneous setting of the diffusion coefficient, it would be better to refer to the recent previous work by Kubota. In this framework, it discusses that the convex energy defined by the weighted total variation and weighted Dirichlet type integral is considered, and it is observed that the subdifferential of this convex energy can be decomposed by as follows. The subdifferential of the singular total variation and the subdifferential of the Dirichlet integral. Now, by using these advantages, we can update the result of the solvability by taking into account the H2 regularity of the component of theta. Especially in the continuous dependence, we can add the strong convergence of the component of theta in the strong topology of C1. Therefore, in one-dimensional setting, we can suppose the uniform convergence for the derivative of the component of theta. Now, based on this, let us come back to the limiting necessary condition. In the one-dimensional case, the relationship as a necessary condition is given in the form of equality. However, even in one-dimensional case, we still have the unclear terms denoted by Guzai circle and theta circle. Now, let us focus on the component of theta circle. Theta circle, roughly in rough sketch, theta circle is expected to be some diffusion of some flux, including the composition of Dirac delta and the derivative of the component of theta. So as a function, this term should be said ill-posed, and it should be distribution. However, in rough sketch, we can expect that support of this term could coincide with this blue region. That is a 0 point of the derivative of theta. Here, under one-dimensional setting, we can say that the derivative of the component theta is continuous, and approximating sequence approaches to this in the uniform topology on omega bar. Therefore, in one-dimensional setting, we can say that this blue region corresponds to the closed set of locally constant parts of the component of theta. So in physically, we can imagine that this blue region corresponds to the part of crystalline facets on grains. Therefore, the complement of this blue region corresponds to an open set corresponding to a neighborhood of grain boundary. Now, based on this, we obtain the following theorem D. This is a final main theorem. Let us take any function rho belonging to C1 global and W1 infinity global, satisfying this property. That is, rho and its derivative takes 0 at the origin. Then we can characterize the limiting and necessary adjoint system by the system of the following time discretization scheme. Here we note that the composition of rho of the derivative of theta is multiplied all of time discretization scheme. Also, on the neighborhood of the grain boundary, the ill-posed diffusion vanishes. Moreover, for another unclear term denoted by Guzai, this Guzai has an expression what we expected. So, on the neighborhood of the grain boundary, we can reformulate the limiting adjoint system as follows. Now, here is a sketch of the proof. The essential difficulty will be in the computation of the second equation of the adjoint system. And the principal part will be expressed by this integral. Here, by the setting of rho, we can restrict the integral domain by this blue region, independent of epsilon. So we need to show the strong convergence of this red term somehow. So we divide the proofs in two steps. The first step, we suppose that the support of rho has a certain distance, delta circle. Then, by the uniform convergence of the derivative of theta, we can see that on this blue integral region, the modulus of the approximating gradient of theta is supported by a positive constant. And by using this raw estimate, we can prove the convergence, strong convergence of this red term going to zero. This implies zero convergence of the principal part. And after that, we can prove the theorem by a standard method of calculus of variation. In general case of law, we can obtain the result by means of approximating argument of law. Now, here are future problems. As the next thema, I am thinking to deal with the optimal control problem for anisotropic Kobayashi-Wallenberg type system. Although the state system will be quite tough, I think I can do something at the level of time discretization. Next, I would like to extend the current setting more practical one. For example, coupling system of fixed cardinal model. And I have several issues. And maybe the time is just stopping time. I stop here. Thank you very much for your attention.
Thank you very much for your very interesting talk. Are there any questions and comments? Please unmute or please chat or unmute. Oh. Are there any questions? Maybe let me ask a few questions. In your argument, do you always need new the parameter in front of Laplacian? Always new is positive?
Yes. For the necessary condition, we need the presence of nu. If nu going to zero, then estimate grow up.
I see. And the second question, you mentioned the decomposition of subdifferential.
Yes.
Could you show the slide? I don't remember the page.
Yes, this one.
Yes. And this is just for 1D or multidimensional?
Currently, I could
decomposition itself, for example, Kubota's result.
Yes, this result is just for 1D. Liuka and Murphy, I found a previous study by Liuka and Murphy, which dealt with a higher dimensional case, but they suppose square type anisotropy. This is quite restrictive case. So in general, higher dimensional case looks difficult.
I see. Thank you very much. Are there any comments and questions? Daniel, please.
I have a question. So is it right that the H2 regularity result is only true in dimension 1 or also in higher dimension?
In my conjecture, we can obtain H2 regularity in higher dimension case.
The interesting thing is that Professor Giga and his collaborator, they were considering also recently, just last year, an equation. It was one Laplace operator plus the P Laplace operator equation, and there they get C1 alpha regularity. Is it right, Professor Giga?
Yeah, first we get for just convex solution. But recently, Tsubouchi extended it for any data, I think.
Any setting. Very recently then. Yeah.
Very recent, Tsubouchi, yeah. I think he's here, right? Tsubouchi-san, are you around? I'm not sure he's around or not.
Okay, so because, and that is the thing why I'm, okay, this is a system, it's a much more difficult situation, but at least in this equation with respect to the second equation in your system, there is a regularization effect given by the Laplace operator. So I guess there should be higher regularity on the solution. That's why I'm.
Yes, can be, yeah. Yeah, the regularity theorem by Tsubouchi is, I think, C1 alpha regularity for such equation.
But he has a Laplace operator, so I mean,
Laplace one, maybe much more, but at least his proof. Yeah, Laplacian plus 1 Laplacian U plus P Laplacian U equals something, good data. Then U is a C1 alpha. We prove it just for convex weak solution. But now he improved it. It is significant difference, significant improvement for any weak solution. So we hope this works for your setting.
Yes.
Are there any further questions? Yeah. Maybe I have one more question. How do you handle with modulus of gradient theta I minus 1 part in the first equation? What I mean is there's a term for, there's the equation for eta. You have 3 equations. You have an equation for eta.
Eta, for example, here?
Yes, this system. Yes. How do you handle this term? If you take dual, it's just a matter of choice of continuous function. I'm a little bit confused about how to
eta is positive. Sorry. If eta is positive, we can deal with about it as a usual function. If eta is equal to 0, we can deal with this term as a weighted measure of the total value.
I see. And dual system is okay for such problem.
Dual of H1, dual of H1 intersection L infinity. It should be. Dual of H1 intersection L infinity.
I see.
Not Hilbert space.
Okay. Thank you very much. Are there any further questions? If not the case, I would like to thank speaker again. Thank you very much, Professor Shirakawa. And I think coffee time will follow from 4 in Sydney, but 2 in Tokyo time. Okay, thank you. And this coffee room URL was sent, I think. Daniel, is already sent? Coffee room.
Everybody received a second email with a link to the coffee break.
Second email.
Start now immediately after this talk. And please, everybody feel warmly invited to join the coffee break.
Okay, thank you very much. So we look forward to meeting you in coffee room. Okay. Yeah, good.
Okay.
So we are,
Okay.
we close the session. Yeah. Thank you very much for participation. Yeah.